Hi, I'm Anders Rundgren. Today I'm going to talk about some of the technology underpinning the open banking wallet and its related infrastructure. If you're rather interested in more user-oriented stuff, you should look into the payment and enrollment presentations. Note that I said some of the technology. There's quite a bunch of other pieces, but they are not necessary for understanding the core concept, which is the goal for this presentation. Okay, here we go. In the dual mode slide, you'll find something called Dedicated Payment API, which is the actual foundation for the wallet. The Dedicated Payment API depends on a locally trusted service that is logically running inside of the bank itself. This service only utilizes existing open banking AIS and PIS method to form this new and quite simple dedicated payment API. Couldn't the wallet just call open banking APIs directly? No, it cannot, because current open banking APIs are based on OAuth, which is a service-centric scheme. Wallets, on the other hand, are client-centric. This has major implications on everything, from security to user experience. Why not integrate the dedicated payment API directly in the bank? Well, that's of course technically possible, but is also unrealistic since it would require an implementation task of the same magnitude as open banking APIs, and that in thousands of banks. Timely upgrades of such an API would be a true nightmare. Compared to that, reusing the massive investment in open banking APIs seems like a pretty cool idea. This arrangement also reduces technical risk, since the open banking APIs are already used and tested. The current proof of concept implementation of a locally trusted service is actually really simple, but should still work with other banks having the same flavor of open banking API. Note that the slide says that the open banking API is unmodified, but doesn't use SCA or consent. How can this even be possible? You're right, something must definitely have changed. However, the open banking APIs are indeed unchanged. It is the addition of another security mode that is only permitted for local access that is the new thing. In this mode, there are no requests for user consents. Question: how can you avoid user consents? Well, that's the easy part. The dedicated payment API never exposes private data to third parties, so there is simply nobody to give consents to. That SA isn't needed either is because the open banking API is invoked by a locally trusted service. Doesn't that mean that the payer is unauthenticated? That would be terrible, but fortunately that is not at all the case. The dedicated payment API builds on a security concept that is already used by billions of people, the EMV standard. The way EMV supports SCA was actually established decades ago. With the pre-configured account identifiers used in EMV, you also completely eliminate the need for third-party access to live account information. This is, by the way, how Apple Pay works. Yes, EMV also provides an excellent user experience. However, unlike Apple Pay, the open banking wallet does not implement the EMV standard as written. Why not? Well, EMV was created for resource-constrained smart cards and have a security model which is unsuitable for the web. Therefore, the open banking wallet was designed from the ground up for mobile phones and to be usable in any payment scenario, of course including the web. The end-to-end security slide shows the core of the open banking wallet, including the dedicated payment API. The system essentially works like this. A payment operation starts by the merchant system invoking the wallet with a payment request. This request is then shown in the wallet UI for the user to authorize with a PIN or biometric operation. There may be a step in between here. The payment request also contains a list of supported payment methods, which are compared to the cards stored in the wallet. Only the cards which are matching are displayed to the user to select from. After the user have authorized the payment request, the wallet application takes the request data and processes it with the keys and data associated with the selected virtual payment card. First, the wallet computes a hash of the payment request and puts the result in an authorization data object together with other information like the account ID. Then the wallet signs the authorization data using the signature key. The purpose of the signature is both for authenticating the card or cardholder as well as for making any tampering with the data detectable. After the data has been signed, it is encrypted using the encryption key. Note that the signature key is unique for each virtual payment card, while the encryption key is shared by all customers of a specific bank. The reason for the latter may not be entirely obvious, but without key sharing, each customer would be recognized by a static identifier, which goes against privacy by design principles. After the signing and encryption operations, the resulting authorization object is returned to the merchant system together with a clear text service URL to the user's bank. That's right, the merchant system does indeed get the name of the user's bank. Now the merchant system puts a copy of the original payment request and the received authorization data into a payment order object and sends it to the user's bank for fulfillment. Finally, the payment order is processed by the user's bank, which involves a bunch of steps as shown in the figure. The comparison of the hashed payment request with the user's authorized copy is necessary because it is the merchant that requests a payment, and the only party that can perform this matching is the user's bank due to the end-to-end security scheme. Although not shown in the slide, a credential database is also a crucial component since it holds the authoritative list of enrolled virtual payment cards. One of the most important features enabled by the shown authorization flow is that the wallet doesn't have to bother with payment method specific data like merchant account ID, etc. Such data is exclusively dealt with in step 4 and is put into the payment order outside of the wallet communication. This keeps the wallet footprint small and supports new payment methods without revising the app. As you can see in the slide, a payment method is just a URL. Now you probably wonder how the merchant authenticates to the bank. Well, that's not a part of this presentation, but is covered by various documents on the Saturn site. There you will also find descriptions of discovery services, which permit extending APIs in a dynamic but still reliable manner. Calling this a wallet is actually a bit limiting, since the goal is to eventually make existing payment terminals redundant. This is beyond what Apple Pay does, since it is based on card protocols, which depend on specific payment terminals. Note that Alipay and lots of other systems out there do not build on card protocols. They were built from scratch for mobile phones and the internet. The high-level end-to-end secured 360-degree web protocol may sound like pure marketing BS, but it just means that the very same protocol and security solutions are used for all merchant-initiated payment scenarios. The idea behind that is to reduce integration costs for banks and merchants, as well as creating a more versatile system for consumers. The universal approach, though, affects user experience. If you fill up your car at an automated gas station, the payment authorization display should adapt itself to that, like in the presentation. Unfortunately, few, if any, of the open banking APIs currently support reservation of funds, so this feature will have to wait a while, although it is fully implemented in the dedicated payment API and wallet. Thank you for listening.